All right, we're going to do a quick look at equilibrium shifts, or Le Chatelier's principle, which is a response to stresses on an equilibrium system. So I've got an example here. We've got SO2 reacting with O2, so those are my reactants. And then I've got SO3 as my product. But this pattern holds true no matter how many reactants you have, how many products, okay? We want to think about the reactants, the products, which way are we shifting? And a way that I solve these problems is to think about the playground toy, teeter-totter or seesaw, where you would put a couple kids on one side, balancing out a couple kids on the other side. This is a simplification of the concept, but it works for figuring out which way we're going to shift. So let's go down to our questions. For each change below, which direction will the reaction shift to reestablish equilibrium? So we're saying this is a 50-50 equilibrium situation, so where things are balanced. So let's take a look at decreasing O2. So if I find O2, here's O2. If I decrease O2, I notice that that's on the reactant side. So that would be like if these two kids here run away and they go, say, play on the slides or something, okay? Decreasing O2. We can see now that we're out of balance, right, on our seesaw. So in order to fix that, we need one of these friends to scoot over here, and now we will be balanced, right? And so that shift was, we need to take some of what's on the product side and shift left over to the reactant side. So we could say shift left, and another way we might say that is towards the reactants. Basically, we need to replace, when we shift, we need to replace what we lost, okay? So let's go back to our starting point again. If we had our 4 kids, okay, let's look at our next scenario. Switch colors here. So increasing SO2. So I find SO2, here's SO2, all right? So if I'm going to increase that, that's on the reactant side. So that's as if I increase what's on the reactant side, all right? Now I can see that I'm not balanced, right? I'm not at equilibrium. And not all equilibriums are 50-50, but we're making that assumption. Things are not even. So in order to fix that, I need to take one of these little friends here, oops, and scoot them over here. Now I can see that I would have 3 and 3. And so what I did is I shifted towards the right, and that was towards my products. Okay, so I initially had more reactants, and then some of those reactants converted over to products. Now we're back at equilibrium. All right, last one. And grab a different color. So decreasing SO3. So here's my SO3. All right, and let's just say, let's get rid of these extra. Get rid of a bunch of these kids. So we've had a change at the playground. Now we're here. All right, so we are balanced. Now we decrease SO3, so that's on the product side. So we're going to decrease these kids on the product side, decide they're going to go run over somewhere else. So there's no one on the right side now. And so in order to fix that, I need one little friend here, oops, to scoot over here. And now I've become balanced, right? So what happened was someone scooted to the right, and so we shifted right, again towards the products. And so what you'll notice is we only ever have 2 situations. We either shift left or we shift right. So whatever you do, you're trying to either replace what you decreased, or if we increased something, then I think about, because it increased, I want to lower it back again. So that means shift some stuff over to the other side. So hopefully that helps you picture kind of some of the shifts, and this applies to so many different types of reactions.